Hello and welcome back to the Nanochat series where we're continuing off where we left in the second part today of GPT.py. So one revelation that I had since 2 days ago when I recorded the last episode was that we did RMS and ReLU incorrectly. Well, of course, ReLU was done incorrectly, so I'll show you the two implementations that we can do. So one of them is actually really quite elegant in my opinion, even if it might not be efficient, but I'm not too sure at all how the PyTorch backend works. But this is one ReLU implementation, which is saying for every single value in X, because the multiplication in tensors for PyTorch broadcasts, which means it applies on every single element. This is my understanding. So for every single element X, if that element of X is greater than 0, then this will be equal to 1, and then you just multiply it. So essentially you're multiplying everything that's greater than 0 to 1, and everything that's less than or equal to 0 by 0. So you could also equivalently have this, and it would have the exact same effect, because if you multiply 0 by 1 or 0, it doesn't matter. Okay, and then there was also another one, which is called torch.clamp. So I'm not even sure why this exists. If it, okay. I was going to say if it behaves exactly like ReLU, but in fact, the only difference between this and ReLU is that it also has an upper bound. So you can specify an upper bound and a min. So like, I guess in this case, not I guess, but right, max would be none and then min would be 0. But, and the out would just be in. Because if you are out, or actually, hold on, clamps all inputs in, yeah. If you are outside of the range, then the output tensor. So the output tensor is just the input tensor. I don't know why I'm confusing everybody as well as myself, but I think that this is much more elegant. So let's just do this. Okay, and then the one other thing is that you can apparently add a torch.compile decorator here to make this more efficient, and in particular to optimize given model size function using torch demo and specified backend. If you're compiling a torch nn.module, you can also use torch nn.module.compile to compile the module in place without changing structure. In any case, in fact, I made a message on the Nanochat repository, and Andre Karpathy told me an answer that if you want to have these implemented essentially from scratch, then you need to use torch compile. But then for attention, it is not going to be possible because of the fused kernels that are used in PyTorch when you use like the actual functional scaled.product attention that comes in the library. So maybe what we'll do is that we'll implement attention from scratch and then end up not using it and just using the PyTorch version. But we're not doing that in today's episode anyway, so we'll just put that aside for now. And then one other thing I wanted to quickly do is at least initialize all of the I forget what you call, like these are elements of the class. So we have, yeah, the layer. I just copy paste it because who wants to watch me type these things one by one? That's not necessary at all. Just a bunch of configs that are necessary for the model. These assert ones are the most interesting. So what's happening here, it's saying that you have to make sure the model dim divided by the number of heads is equal to, the remainder is equal to 0, sorry. And then there's at least as many, that the number of Q heads is greater than or equal to the number of KV heads, that the number of heads that are Q heads is, the remainder of this divided by the number of K heads is 0 because it should be a multiple, just like we have it here, 6, 3, 2, or 1 in this case. And then we can also just create our 4 learned matrices which are used in attention. So attention is denoted the softmax over the Q matrix times, or matrix multiplied by the K matrix transposed. Then you divide by the dimensionality of K, and then you multiply by V. In any case, we're just setting these matrices up to be of dimension model dimension by head, number of heads by head dim, which is the same as model dimension, but there are n heads, so we need to specify like this. And then we also have the projection matrix, which takes the final output of attention and then projects it back to the dimension of the model, which in this case is 768. And just like everything here, we don't use bias in linear layers. So this is everything for self-attention. Now, the next topic that I wanted to cover in this video is the inference. So if we come down here, we can just skip to a method of the GPT class, which is going to be called, let me verify the name, generate. So pretty standard name, def generate and self. And what we're going to do first is attach a decorator to this method, which is the torch dot, oh, that's not well, torch dot inference mode. And what this does is it's a context manager analogous to Nograd, which just means that it's not going to accumulate gradients because we're just doing forward passes. That's all you need to know. And this just makes the throughput faster. It gets better performance by disabling a bunch of things that we don't need when we are just doing a forward pass and inference. And what are the parameters of this? There are a few. So there's tokens, max underscore tokens, temperature, and top K. So these are default parameters, these last few. Temperature is 1, top K is none, and then there's also seed, which is used for, what is it used for? We'll find out anyways, I forget. And yeah, there's nothing else really to say other than let's get started here. So we assume that the tokens, which is just a list of IDs, right, is a Python list for the sake of simplicity. So we go from tokens to list, or no, we just check if it's a list to insertion, and then we will do device equals self, right? Self dot, has this been implemented yet? It has not. So we'll implement the device method because it's extremely simple. So what is it? It is def get underscore device, and then it's just, oh, forgot the self and the colon. What an amazing thing. And actually, I just realized here that I forgot to set this to config. So that's a good programmer move. And then this is just return. All we have to do is return one of these three weights, or essentially components of the transformer, because we assume that they're all on the same device. So you wouldn't want to pick blocks, I guess, since it's really big. I think you just pick LM head or word to embedding. Karpathy picks word to embedding, so we're going to do the same. Self.w.te.weight and .device. Okay, so this just returns the device that this is on, which is the same as everything else. And then we can just call this method. And this is required, well, it's required to see where we're actually performing the inference. And then if temperature, right, is greater than 0. So I think if you set temperature to 0, then I think it's greedy decoding, but that is correct. So if you set temperature to 0, you literally just pick the most likely element. So if it's not, then we need to set up a random number generator. So this is going to be used in order to set our seed, which I still have no idea what it does, but we'll find out. This is why we need the device, because it's going to be on the same, like our random number generator is going to be on the same device as the rest of the tensors, so we need to set it there. And then we do it from a manual seed, which is just seed. Okay, now we can take our IDs and convert them to a torch tensor because they are Python lists right now. Ooh, can't spell. Okay, so it's the tokens themselves. The D type apparently is a torch.long, and if I'm not mistaken, this is I think this is 32 bits. If it's 64 bits, I'll be thoroughly surprised. But it's been a while since I took the low-level course, so I forget what a long is, because I think a double long is 64 bits or 2 bytes. Okay. Oh, and yeah, literally this is just for the batch dim, right? The brackets around tokens is just to add the batch dim. And then now we do generation for the number of tokens that we specify here. So like this is the maximum amount of tokens that you want to generate. So we do this that many times. We get our first logits, which is just the result of the forward pass, which we will implement and then forget about it. Def forward self. Is there because I always see them say unimplemented. No, I've seen people say like raise unimplemented error, but maybe you have to import that from a specific library because it's not popping up in the type-ins. So we literally just get the logits by passing the IDs through the forward pass of the network, and then we only want the logits for the last token. So in order to get those logits, we have to just do -1, 1. Oh, sorry, I'm doing this in the wrong way. It's -1 because it's batch. Let's remind ourselves what the dimensions are, because this is batch by sequence by embedding. So we want the last one here and everything for the last one, which is to say everything, the last one, and then we need to actually have these separated by commas. So everything for the batch, only the last token, and then once again, everything for the embeddings. And then the next step is to check if top K is not none, so that we can sample the top K instead of the entire distribution. That is, so top K, as if you don't remember, is taking the tokens with the high, like the top K tokens with the highest probabilities, and then sampling only those ones. So let's say if you have I am the, and then there's like cat, dog, sheep. If you do top K equals 2 and cat and dog are the most likely, then you only pick between cat and dog instead of picking between sheep as well. Okay? So if top K is not none, then we will just grab torch.topk, which conveniently encapsulates all of this logic for us. Top K. And why are we like dropping this? And then why are we dropping the second value that it returns? It's because not only does top K return the top 2 or however many objects you have, it also returns the indices, but we don't want the indices. We only want the right. It's an output tuple of tensor log tensor that can be optionally given to be used as output person. We only want the values, right? Values, indices. Anyways, what are we putting inside of here is the question we're all wondering, and it's just the logits, of course. And there's just a small safety check that we can do, which is to say that if somehow the user specifies top K to be more than the tokens that are in our final logits vector. Well, actually here, this might be, this is not sequence, I'm very sorry. This is vocab size. And if I'm mistaken here, then I'm really embarrassed. So let's come back to this now. Let's come back to this later, and let's just continue on for now, because I realized that, right, once you get the logits vector, okay, let's fix this now, because this is really important. So, right, the embedding vector x is dimension sequence length. And if this is obvious to you, then please just skip ahead, but it always becomes elusive to me, so I have to write it down to make sure. If this is sequence length by embedding dimension, then we multiply it by a vector which is embedding dimension by vocab size, and then this gives us a sequence length by vocab size vector. So that is correct, and we need to change this therefore to a sequence length by vocab size vector. And this still makes sense that we pick the last element here, because we pick the last token in that sequence length by vocab size vector, and then we'll have a probability distribution of the entire vocab size, which we will choose from. And then here, once again, it's saying that if the top K is somehow greater than the vocab size, then we want to pick the vocab size and not the large top K, which I guess is just prevent something stupid from happening. So in this case, we'll do logits dot size -1. I think you could just index it by -1, literally to the last element, but we want the size, so we don't want the last the value of the last element. Okay, and I forgot to say that this is not done. Okay, and now that we have the values of the top K, we can apply torch.where, which is a very nifty function. Let's read the description. Return a tensor of elements selected from either input or other, depending on condition. The operation is defined as the condition, which in this case is what you would call a Boolean tensor. And what this Boolean tensor does is it compares the logits, which is of dimension batch by 1 by vocab size, to the values of the top K. And top K, let's see, what is the size of top K? So we still have the batch dimension. That hasn't changed at all. Okay. And then we also still have the sequence length. That's 1. Or yes. And then the vocab size. No, the vocab size is now K. There you go. So this is the difference between the two. So we have this new vector, this new tensor, and we keep the batch and the dimension 1. We don't touch that, but we grab the last value in this array, which is equivalent to the kth value with like the lowest probability, or more precisely the logit probability. So this is before that's been softmax, and because it's -1, I assume that top K where represents them, right, returns the top K in descending order. Let's just make sure that's the case. Controls whether to return the elements in sorted order, bool optional. Where is the default value? Yeah, sorted equals true, and I assume it's in descending order. So this is essentially giving us the last top K, which is the threshold. If you have a logit that is lower than that, then you're not on the top K. And then this gives us a Boolean tensor over the logits to say whether or not true or false is this a part of the top K. And then if we come back to the definition here, when true, yield input, otherwise yield other. This is the case here. So if it is true that the logits is greater, if the logits is less than the last top K, then you give negative float. And then if not, then it's logits. And it's worth noting negative float is done because when you softmax the float, you get 0. And if you wanted to do a greater than sign here, then you just have to flip the order of these two. And then you may be confused because this is like a scalar and we have a tensor here. So is it going to make like a scalar composed of a tensor? Because you want to have the dimensions to be the same, right? But it actually is given right here, right? It's going to be value if input is a scalar, or value selected at indices where condition is true. This means that the tensor will be broadcasted to the shape of condition input other, which is to say, like, whichever the scalar is, it will just be mapped to the dimension of the other inputs. But this means that at least one or at least two of the tensors here should be the same dimension, and then one of the outputs can be a scalar. So there you have it. It's almost like masking, but it's like a convenient type of masking. And then now let's deal with the case where if temperature is greater than 0, so everything except greedy sampling. So in this case, what you do is you divide the logits by the temperature, and let's give a quick little crash course on temperature. So the closer temperature is to 0, the greedier your sampling is, because if your temperature is 0, you would actually get a error, right, dividing by 0. But it's because the fact is, as you go to the limit of temperature approaching 0, then your logits explode. And because your logits are exploding and you're exponentiating them, then the greatest logit will almost like a like a race to the death, it will be the one that rises the most, and essentially every other value, even if it's slightly less only, will like look like nothing compared to it. But then conversely, if you have a really high temperature, let's say of the like in the extreme case, you have temperature equal to 1,000,000, then you're dividing all the logits by 1,000,000. All the logits are essentially 0. And then once you put these like 0 to the power of e, then you'll get like something close to 0. And then once you do e to the power of 0, then you'll just have like 1 for all of your values, and then it'll be a uniform distribution. So there you go with temperature. So we divide by the temperature, and we set this to the logits. Then we can get our probabilities by doing f.softmax, and I really need to import f from torch.nn. I tried to avoid it, but I realize now that we definitely need it. Dot functional as f, and then logits, and then we do it on the last dimension, because last dimension is over the vocab size, which is all of the different probabilities, but this could also be over only k values if we did top k sampling. Dimension equals -1. Okay, so that's for the probabilities. And then now we can actually sample for our next ID, which in this case is torch.multinomial, which just means sample from a multinomial. I guess this is just a probability distribution. Don't ask me what multinomial means, because it's been a while since high school calculus. And then the number of samples that we pick is just 1, since we're only sampling 1 token at a time. And then this finally, now I realize, is where we need the random number generator, because right, if we're not doing greedy sampling, then we're sampling from a distribution, and then you need an element of randomness, which is established by this RNG. Okay, but then if it isn't temperature equal to 0, temperature is equal to 0. Sorry, if temperature isn't greater than 0, then we just do a simple torch.argmax, which is to say grab the largest logit from logits, and the dimension will be equal to -1. And since it is argmax, just like me, it will try to collapse the last dimension, but we want to do keep dim equals to true to maintain that last vocab size dimension, so that it doesn't just become batch size times 1. Okay, and then there's only 2 more things here to do, which is to say IDs equals torch.cat. So we're just appending. Torch.cat is essentially list.append the current IDs and the next IDs, and it's just plural because we could have multiple batches. And what dimension is this along? It's along the second dimension, so dimension 1. And why is this the case? Let's look. So we have IDs, right? And our tensor is of batch by sequence length by vocab size. So we want to add the IDs on the sequence length vector, because, right, we have a tensor of up to sequence length and maybe 3. It says I have 3 cats. Then you want to add cats to that dimension, of course. And then we'll just do token equals next IDs. So we want to actually grab the token that we generated, because when you generate a ID from next IDs, then you'll get some type of PyTorch object, and then if you want to grab the actual value, you need to call item. And then since this is actually me an iterator, so yield just means that it's stateful instead of stateless. So this is to say that when you do return on a Python function, you lose all of your local variables. Whereas if you yield something, then this is exactly why we're doing a torch.cat and extending our IDs, because this IDs list will be persistent across function calls, and it will always be the same. And the same goes for like the C and then temperature. This will all be stored as a local variable and will not be forgotten after the function returns, but it's not returning, it's actually yielding a token. So yeah, this is the entire torch.inference_mode method. So to recap what we did today, we made this function, which is definitely the most technical, and then forward, which we haven't implemented yet, the device, which is really simple. We added the parameters for self-detention. We fixed the ReLU from yesterday, and then we also added the torch compile to those two. But we'll see when we go into training if this is slowing it down too much, which we can do through some profiling. Then we'll have to just use the standard implementation from torch.nn.functional. Okay, so thanks for listening, and see you in the next video.